Let's derive the angular velocity function when we know the angular acceleration function as a function of time. First, let's list the initial conditions of the problem, and those are that at time equal to 0 seconds, the initial angular position is 2 radians, and the initial angular velocity is 5 radians per second. By definition, the angular acceleration is calculated as the time derivative of the angular velocity, so if I rearrange the terms in this expression, I can express the angular velocity d omega as the product of the angular acceleration alpha and the time dt. To find the angular velocity omega, I need to just integrate both sides of this expression. And so integral of d omega is equal to integral of alpha dt. So the left side of this relationship is simply omega as a function of time. And then on the right-hand side, I replace alpha with its expression, which is 5t to the third power minus 4 times t. So now I need to do that integral on the right-hand side. So the integral will look like so. Integral of 5t to the third power minus 4t dt. I will split that into two integrals. So an integral of 5t to the third power dt minus an integral of 4t dt. So when the integrals are done, the first one yields 5 over 4 t to the fourth power minus 4 over 2 times t to the second power plus a constant. So the constant comes in here because these are integrals without limits, and so that is part of the solution. So the question is, what's this constant equal to? The constant can be determined from the initial conditions of the problem. So if I replace the value for the time t with 0 seconds, I get for the angular velocity that the constant 1 is equal to 5 radians per second. And so putting everything together gives us an expression for the angular velocity as a function of time, and that is 5/4 t to the fourth power minus 2 times t to the second power plus 5, and the units would be radians per second. So the next step would be to find the expression for the position as a function of time, omega of t. Theta of t. So the definition of the angular velocity is the time derivative of the position function, the omega. So omega of t is equal to d theta dt, and from here, by rearranging the expression, I can isolate the theta alone on the left-hand side, and on the right-hand side I have omega of t dt. So in order to find an expression for theta as a function of time, I must integrate both sides of the expression. And so the integral looks like so. Integral of the theta is equal to integral of omega t dt. Replacing omega of t with the expression that we found previously, the integral becomes integral of 5/4 times t to the fourth power minus 2 times t to the second power plus 5 dt. In order to do the integral, for simplicity, I'm going to split the right-hand side into 3 integrals. So theta is equal to an integral of 5/4 t to the fourth power dt minus an integral of 2 times t to the second power dt plus an integral of 5 times dt. And when you do the integrals, you would get 5 t to the fifth power divided by 4 times 5 minus 2/3 t to the third power plus 5t plus another constant, let's call it constant 2. So constant 2 can be determined from the initial conditions of the problem. And the initial conditions state that at t equals 0 seconds, the angular position is equal to 2 radians. So if I substitute 0 seconds into the expression that I've got from the integration, I get that the angular position is just equal to constant 2, and that should be 2 radians. So constant 2 is equal to 2 radians. So replacing everything in the expression for the position function, I get that theta of t is equal to t to the fifth power divided by 4 plus 2/3 t to the third power plus 5t. And here I need to add the value for the constant, and so finally that's plus 2 radians. So one more time, the position function is t to the fifth power divided by 4 minus 2/3 t to the third power plus 5t plus 2, and the units would be radians.